to have what we hope to be our first annual invited student presentations. We thought this would be a really, really great way to showcase a lot of the great work that's being done, either as undergraduates, grad students, or in collaboration among the different organizations. So tonight you'll see that it's fairly heavily skewed towards folks that have worked with the National Weather Service and State College, but we certainly want to continue to expand this out. And I'm really excited to have some good friends and people that I've had the pleasure of working with over the course of the past several years of being here in State College. So the way tonight's going to work, we're going to have 6 different student presentations. You likely saw the invitation in the email. Dylan Steinkruger, Nicole LoBiondo, Christopher Long, Jacob Morse, Callan Parker, and Grant Lashott. And each student is going to present for about 10 minutes. Not going to be timing you, not anything too crazy. If you start getting 15, 20 minutes, we might just have to mute you and say, okay, we'll open it up for questions. But we'll have a little bit of time for question and answer at the end as well. Try to keep that, a couple minutes or so. And then ideally we'll kind of wrap up by, I'm thinking 8:30 is probably fairly reasonable by the time we have 10 minutes for each person, and then Q&A after that. Any questions on how tonight will work? Okay. Well, Dylan, are you cool with going first? Okay. Yeah. I will. I'll go ahead and read Dylan's title of his talk and then his bio. So Dylan is going to be presenting his talk, his grad work entitled "Utilizing Artificial Intelligence in the Tornado Warning Decision Process." Dylan is a PhD student at Penn State University and previously received his bachelor's degree in 2018 at the University of Nebraska-Lincoln before going to Penn State and receiving his master's degree in May of 2020. His research focuses on the intersection of artificial intelligence and severe weather prediction. Currently, Dylan's work focuses on developing an artificially intelligent system to produce automated tornado warning guidance to assist in the tornado warning decision process. So without further ado, it's my privilege to invite my friend Dylan Steinkruger, who, did he just disappear? Uh-oh. I guess stage fright really got the best of him or something here.
Sean, don't you live with him? Can't you give the talk?
I'm back. Sorry. For some reason, I just updated my MacBook, and then it said, you can't share your screen, and then it said, click this to share it, and then I clicked it, and it shut me off. So I'm not, maybe Paul can give the presentation for me, but
yeah. Well,
hopefully you can see it now.
Yep. Take it away, Dylan.
Okay. All right. Well, thanks for the introduction and for the extravagant intro to this whole talk. So yeah, as John mentioned, I'm Dylan Steinkruger. I'm a graduate student at Penn State. So I'm going to be talking a little bit about some of the work we've been doing trying to merge artificial intelligence and tornado warning decision making, if you will, together. And so before I do want to get into this, I definitely want to give some acknowledgments as well to my advisors, Paul Markowski, who's here, and George Young as well. So let's see if I can click into this. Okay, so I'll motivate this very briefly, just with the idea that tornado prediction is no easy task. I think it's a challenging problem for many reasons, one of which is that the processes leading to tornadogenesis or tornadogenesis failure are not entirely understood. Even in well-observed storms, we can't always go back and say why a storm did or did not actually produce a tornado. On top of that, rapid decision-making is required on the warning timescale. Quick decisions have to be made. There's no room for error, particularly with consideration to lead time, with storms rapidly evolving, and radar features rapidly evolving as well. And then on top of that, the features that are important, different forecasters are going to look at different storms in different ways. And so there's a possibility that, different decisions could be made by different forecasters looking at the exact same storm. And so these are really some of the potential benefits we see, with the utility of automated guidance. One of the first things is really just taking all the data that's available and turning it into some type of concise suggestion that can be updated very rapidly. So radar data is updated every 2 minutes. Sometimes there can be multiple radars looking at a similar storm where all of that information might need to be considered. Satellite data is obviously updating rapidly. Model output now is increasing in its evolution with regard to how rapidly it updates. In some cases as quickly as every 15 minutes. And so really our goal here is designing an AI system that in some ways mimics a forecaster but that's going to make consistent, quick decisions, no matter where it's at, across different parts of the country. No matter, how many storms it's looked at, it's going to make the same decision, and really with this goal of putting another forecaster in the room. And so I'm not going to talk about any of the details of the individual machine learning models or anything like that. I'm primarily just going to show output because I think that's a little bit more enjoyable to look at. But I'll start with this slide. And so this is kind of the raw machine learning model output. This is the probabilities that are being output by individual machine learning models. And I think in some ways, this has some operational utility in and of itself. And some products like this already exist. If you're familiar with products like ProbSevere, I think NSSL even has a product that looks somewhat like this. And so basically what I'm showing here, and I'll pause this for just a second. So over here on the left is just showing the sort of machine learning model's answers to a question of when will a tornado occur. So it's essentially plotting the probability that this storm over here on the right will produce a tornado at some given lead time. And then these red bars going across the screen actually indicate times when this storm over here on the right will produce a tornado. And then over here on the right is showing the track. So it's just showing the probability of where that storm will be. And so you see over on the right, there's kind of that right-hand hook to the storm. As you can see, as this storm kind of progresses and evolves, as this storm actually starts to produce tornadoes kind of cyclically, these probabilities end up kind of maxing out up over 70%, 60, 70, 80%. And then over on the right, as this storm sort of gets entrained in this line, there becomes a little bit more uncertainty with where that storm track is. Those probabilities spread out as well. And so again, you can kind of see that these are the two questions you sort of have to answer to actually issue a tornado warning. You need to know when will that tornado occur, and then where will that tornado occur, so you can draw your warning and determine how long it should be drawn for, both from a spatial perspective and a temporal one. And so, I think there's useful data here. There's a lot of information, with these probabilities that could be useful. But the problem with it is that there's a lot of data here. We're really taking data that's already available and making even more of it in some ways. So, for this question of when will a tornado occur, we can train 15 different machine learning models and have all of these different probabilities. Similarly, on the right, we can have the tracks for all of these different types of storms. It just doesn't seem conceivable that somebody's going to be able to look at this data, also be making their own inferences from the radar data that they're looking at and trying to make decisions with that. So one of our goals has really been trying to take this machine learning model output and convert it into something that's binary and in a lot of ways looks similar to what a forecaster might be issuing, so that it can potentially, prompt the forecaster to issue a warning if one's not currently issued, or if one needs to be extended. And so what I'm actually going to show here are a couple examples of the AI system actually running. So the blue polygons that are going to be drawn on these next couple of animations are those being drawn or generated by the AI system. The red warnings are those that were issued by the National Weather Service on this particular day. And then this green polygon just indicates the area that that the AI system is considering issuing warnings for. And then you'll see some triangles pop up there. Those are just the tornadoes. And so for these first two animations that I'm going to show, I'm not going to point to anything specific. What I primarily want to point out is just the similarity in the warnings that are being issued by the AI system and the warnings that were issued by the National Weather Service on these particular days. And that there's a lot of similarity. In fact, I think that if the AI warnings weren't rounded, you probably wouldn't even know the difference between which ones were AI and which ones were the National Weather Service. And so again, really our goal with this is to create something that looks like what a forecaster would be producing, hopefully giving them some more confidence in the warnings that they're issued, or just an increased amount of situational awareness based on how the storms are evolving, based on what the environmental conditions might be like. And so here, this is again another case down in the Southeast. Very similar decision-making going on by both the AI system and the National Weather Service. So really, this has been a very encouraging sort of preliminary result that in many cases, we get warnings that are similar. We're getting similar decision-making going on by both by the AI system and the National Weather Service. And so I'll point out a couple of individual cases where maybe the AI system performed well. So this is one, it's going to be this southern cell, and these are just still images. Hopefully my video isn't lagging too bad. This is just a still image here. And so what was going on here on this particular storm is that the National Weather Service and the AI system were both warning this supercell. The AI system continued to warn it after it had produced a few tornadoes, and it continues to extend it out to this right. And this supercell is actually starting to track outside of the box that was originally drawn by the National Weather Service. And so you can see 1 minute later, a tornado does occur just barely on the edge of the National Weather Service box, but well within the AI one. And then you actually see just 2 more minutes beyond that, the AI system, the warning that's actually issued by the National Weather Service is basically the same one that had been issued by the AI system several minutes before that. Here's just another case where the AI system issues a warning. This is a case where the National Weather Service does it and a tornado occurs. Again, these are sorts of situational awareness things. Maybe a forecaster wasn't even considering a warning on this particular storm. Maybe they were and they decided not to. Maybe this changes their perspective on it, seeing something like this. And so I'll make sure to show a case here. I've kind of set the AI system up to be this great oracle of tornado warning decision making, but it's certainly not the case. The AI system definitely has its flaws, from false alarms or as I'm going to show in this case, situations where it just stops warning storms. So this is actually a linear system down in Oklahoma, and you're going to see there's multiple tornadoes that form along the leading edge of this sort of QLCS storm along kind of this Boeing segment. The AI system just misses. And so there are definitely cases out there where the AI system couldn't run just independently of a human. That's certainly not what we're trying to create. But again, I think some of those cases that I've shown previously, there is some utility in this guidance. Okay, so what I've shown previously has been some of the work we've been doing on kind of the 0 to 45-minute time frame. But in our discussion with forecasters, one of the common things that they say is they really would like a tool that fits somewhere between, say, the warning and the watch time scale. And so this is some very hot off the press work. This is just an individual machine learning model, so there's no sort of polygons being drawn for this, but it's basically showing where are there enhanced areas of possibility that a tornado could occur in the next 0 to 3 hours within 50 kilometers of one of these points. And so I'll play this out. This is the October 2nd, 2018 day in Pennsylvania. And so you can see in general, I don't think this is too surprising of an event. Fairly enhanced values across kind of this central region where most of these, the tornadoes actually ended up occurring. And I'll play this through one more time. Again, as these tornadoes start to form around 1Z, and I get this kind of loops kind of fast, you can see certainly enhanced values in location where these tornadoes actually occurred. And so again, that wasn't really a surprising case, but one other case. So this is a case I actually chased this past year, June 7th, 2020. And so it was actually an enhanced risk up here, up north of Grand Forks on the North Dakota-Minnesota border, corresponding with where the machine learning model probabilities actually had enhanced values. The National Weather Service, the Storm Prediction Center, put out a tornado watch in this particular case. What's interesting is how this evolves. So, initially, even at 21Z, that's still kind of the maximum area. But if you notice, even at 21Z, there's sort of this region in northern South Dakota that's enhanced. And as we progress over the next hour, over the next 2 hours, and this is about 15 or 20 minutes before the first tornado is going to be produced here in northern South Dakota, really this kind of region of interest has really shifted to the south. And the machine learning models, this single machine learning model, I guess, actually picks up on this fairly decently. And so it actually ends up, this is where most of the tornadoes actually end up occurring in this particular day. And the machine learning model, I think, did a decent job. And again, it's a very preliminary model, hasn't been trained on much data at all, but it did a decent job in this case. And so I think my 10 minutes are up. So I'll wrap up here. There's a lot to be explored, a lot to be refined. The big thing this spring is we get to do some testing with this. Actually had this running this afternoon, and the AI system actually got its first tornado of the year. Today was the first day running it, and so there were some storms down in Florida. So this was the radar scope, extremely dangerous tornado confirmation, and this was the storm over by Damascus. I don't know if that was Florida or Alabama or somewhere down in Georgia maybe. But yeah, I don't know if I think we're taking questions. So thank you guys for listening. If you have any questions, I'd be glad to answer.
Thanks, Dylan. That was awesome. We're also working with Dylan on some lightning applications of this in terms of assisting with on-site weather support type initiatives. So really, really cool stuff. Love seeing the new developments. And yeah, this was a tornado in Georgia, I believe. I guess, yeah. That had like a TDS on it, potential EF2, EF3 based on TDS height stuff. So without further ado, any questions anybody has, feel free to either raise your hand or just unmute yourself and ask away.
Hey, Dylan, I have a question. This is Sonia Miller. so all your training data is just data that's automatically produced, no forecast or modified data or anything like that?
Yeah, so the
Sorry, go ahead.
Yeah, sorry, yeah, you cut out a little bit. Yeah, so what I was showing in those animations is all AI based. There's no human modifications to those at all. That's right.
This is John. So what kind of data is going in there? I know for years, I've worked a couple of tornado events over the years. I'm now retired, but we've got TVSs on the Doppler system in AWIPS for forever. And we found that most of those are pretty worthless. So I'm kind of interested, just from an observational standpoint, it's like, what kind of data is actually going in? Is it real-time model data? Are you adjusting observational data as well and running it all on that?
Yeah, so it's pretty simplistic right now. It's primarily just level 2 radar data, some level 3 radar data, and then some RAP soundings are put in there as well. So there's not a ton of model information that's going in there. The machine learning models tend to rely a lot on the radar observations, maybe in some ways similar to how a TVS works, but maybe the machine learning models are a little bit better at delineating some of these storms, given their thresholds might not be as strict as the TVS thresholds.
Yeah, I took a lot of solace over the years for Dr. Markowski just saying he feels sorry for us having to sit at the radar and issue warnings based on the radar. So that's interesting. There's really not a lot of other information in there. It's just a different way of, I guess, crunching this information.
Sure, and that's something that as we go forward. So there's some other products out there, particularly looking at some of these rapidly updating models, warn on forecast, that we can definitely incorporate. We just need more time to kind of get those things ingested, and hopefully they can improve upon what we've already built.
Well, good. I don't want to feel like I missed something.
Yeah. Thanks.
Yeah, Paul, how about you?
Yeah, Dylan, I was wondering if you wanted to comment on how certain thresholds can be tuned based on proximity to population centers, or if there's some reason to be more trigger happy or less trigger happy in a certain situation.
Yeah, so I can show this slide. So as Paul's alluding to, one of the things we're actually able to do with the machine learning or with the AI systems that we can tune these thresholds. So if you want a really high POD, obviously it's going to come at the cost of more false alarms, but you can have that really high POD. So think days where, really high in tornadoes, maybe you want lead time. Maybe lead time is that factor that's really important. Whereas maybe in a QLCS, you're going to have a lot of false alarms. Maybe you want to lower those thresholds. And so this is sort of an example of that, where these are 4 different AI systems for this particular day. They're all trained to kind of have different thresholds with regards to how they're issuing warnings. And so you can see that all 4 of these different AI systems are issuing different warnings kind of based on those characteristics that we've trained to. And so as Paul alluded to, there's different end users might desire sort of different characteristics. So, a city population might need different characteristics than, just maybe your rural area in the middle of Nebraska, or somebody in a mobile home might want different warning characteristics than somebody in a well-built house. And so with AI, we're really able to do this really quickly, give all these different decisions, whereas all these different decisions probably wouldn't be able to be made by an individual forecaster. So that's one of the benefits of the AI system as well.
Really cool stuff. In the interest of time, I think we're going to go ahead and move on. But Dylan, thank you so much for presenting to us. We really appreciate it.
Yeah, thank you.
If you guys have any additional questions for Dylan, certainly feel free to send him a chat or reach out to him after the fact. Up next, we'll have Nikki. Pete I see Peter's iPad. Is that Pete Young?
Yes, it is.
Are you good to introduce Nikki for us?
Actually, I'm not. I don't have her bio in front of me.
No problem at all. Okay, that sounds good. So Christina, we'll go ahead and have Christina read the bio. Not a problem, Pete.
All right, so Nikki is up, and Nikki has been working at AccuWeather as a meteorologist for nearly 2 years now. She graduated from Penn State with a major in atmospheric science and a minor in climatology. And and another minor in geography. Cloud formations and winter weather are some of her favorite meteorological topics. She's also an avid photographer, a painter, and a snowboarder. She works at Tussey Mountain on her days off as a professional snowboard instructor.
Oh, wow.
So today she will present on relative humidity, climatology, and Dewpoints bombs in central Pennsylvania. So Nikki, I'll hand it over to you and you can share your screen.
Previous record is 7 above.
All right, I'll share my screen here. Thanks for the introduction. That was very nice. Can you guys see my screen? Oh, hang on, sorry. Okay, you guys can see the PowerPoint, right?
Yep.
Okay, cool. Just wanted to make sure. I did this research when I was an undergrad, and I did it through the National Weather Service and State College. What we looked at were the relative humidity, climatology, and these quote unquote dew point bombs that occur in central Pennsylvania in certain weather situations. This is especially important for fire weather forecasts, for when controlled burns need to be done, or so on and so forth with like the forestry departments and stuff like that. So the initial project actually begun in the fall of 2017 through spring of 2018 with Brian Cizik, who's also a Penn State graduate. His motivation really started when he noticed that there were specific spring days where models and like the official forecast from the National Weather Service would badly overestimate the relative humidity. Oftentimes the forecasted relative humidity was high. This has implications, like I said, for fire weather and controlled burns. So we really wanted to dig down deep and see why this happens, and if we could help better forecast them in certain weather patterns. The approach is, it happened a lot, it seemed like in Williamsport, Pennsylvania. Noticed frequent relative humidity busts with the National Weather Service forecast. Brian had identified specific days with the highest relative humidity errors, and then looked at weather features and other parameters such as dry air, intrusions at the surface and aloft to try to identify a pattern that could help explain why this was happening. The findings in that initial project that there are favored weather patterns that could lead to these significant relative humidity busts, and we'll look at these patterns later in this presentation. So the current project, or the project that I was working on with Rob at National Weather Service office while I was volunteering there, we wanted to really focus on ways to improve the day one relative humidity forecast, with the emphasis on the RH values, with a drop of into the 15 to 40% range. And like I said, this has obvious implications for the fire, weather, and controlled burns. Our preliminary research suggested that the general forecast for the RH was too high on high impact fire weather days. So that's a very important tidbit there. The approach for phase one, we wanted to expand what dots we were going to look at to see if this happened anywhere else really across central Pennsylvania and not just Williamsport. So we looked at other NWS observation sites and developed kind of a climatology of minimum relative humidity set, really based on both time of year and the geographic location. And then the phase two of this project that we were doing was to identify any specific days when RH observations showed significant drops, to see how well those days matched up with the identified weather patterns that we found that were lucrative of this phenomena, and then compare the model to the NWS forecasts to actual observations to see how and if we could predict RH better and how it would drop and so on. And then the approach for the phase three portion of the project was to use the results, like I said, to identify and improve the forecasts at the NWS State College office. So phase one, we kind of use this methodology of we use 3.5 years worth of hourly data from 10 ASOS sites across central PA for 4 winters and springs and 3 summers and falls. These are the sites that we included. So anywhere from Bradford to Lancaster were some sites that were included, and of course State College. We found that the minimum RH value each day would occur between 10 a.m. and 7 p.m. And then we counted the number of days the RH fell below these thresholds between 20 and 40%. So here's a kind of a graph that shows the frequency of below 40% minimum of relative humidity. So it looks like March, April, and May, this happened quite often in comparison to the rest of the year. This was the frequency of the 30% RH minimum, and that, as you can see, occurred in March, April, and May, again, with the highest frequencies. And this is for all the sites that I had shown you on that map previously. And then this is the frequency of a 20 or 20% minimum relative humidity drop for, as you can see, they only really happened in March, April, and May. So that really helped us narrow down really what months we were to look at to develop this climatology. And this is kind of for just to show all those graphics all on one graph to show that March, April, May were really the times that we need to focus on and observe the weather pattern. So there's a smaller peak in the fall, as we can see here. It's September, October, November, and that would depend on like the ground moisture conditions, if there was a wet fall or if there was any snow cover at that point, so on and so forth. So this kind of went through by ASOS sites that we had chose. So this was Williamsport. It seemed like, again, the March, April, May, the frequency of 40% or below of minimum RH was really, compared to all the rest of the sites, happened more in Williamsport. And then in Johnstown, just to take from the data set, it happened not as much as in Williamsport, but still happened, as we can see, in March, April, and May. And then that little spike here in the fall as well. So the summary of this is that the low RH percentages occur most frequently at Williamsport by far, and then also Harrisburg and Selinsgrove also had some as well for the most frequent. And the least frequent were down in like Johnstown and Bradford as well, and we can see that based on the colors here on the map. I can't, sorry, John, I just saw your message. I can't go to full screen, so I'm using two separate screens, so then I wouldn't see you guys and I couldn't see messages. So I hope this is okay, the way that this is being presented.
It's been great, Nikki. No problem. Okay,
cool, sorry. So phase 2 of the project, so there's a difference between obviously relative humidity and dew point. So we wanted to also see these dew point bombs, as we called them, where dew points drop dramatically over the course of only a few hours and then also rise again over the course of a few hours. So we define them as a specific dew point fall during the day, followed by a rise in the evening. So falls of greater than or equal to 10 degrees Fahrenheit, and then a rise of 5 degrees equal to or more than. So these are not necessarily associated with specific relative humidity values, but these almost always push the RH values down into more critical fire weather categories. These bombs, quote unquote, often equate to RH falling 10 to 20% lower than expectations. So kind of understanding the dew point is also important for these forecasts, especially for fire weather. So this kind of shows, so this was the NWS dew point forecast, the blue line, and then the actual dew point we can see was the red line, and there was an error of about 13 degrees from this particular event that happened in May of 2018. So this really shows that this, this is an issue, and this is kind of gave us more motivation for the project. So there's these errors that happened. It's difficult to predict these, and they tend to occur over very small geographical areas. And it's very rare for computer models to pick up on these. So we kind of continued, let me see your currents. So these are like the weather patterns that we found that kind of showed us what these dew point bombs are associated with. So type 1 weather situation is a building Canadian high, breezy winds, and clear sky in the afternoon, breezy north flow around 10 to 15 miles per hour with gusts of 20 to 25, and cold air advection the lowest 5,000 feet. When these features are occurring, we next must look at the conditions near the top of the boundary layer and a few thousand feet above the surface for other noteworthy features. This is the second setup that kind of showed these dew point bombs happening, was an approaching warm front with light winds with a retreating Canadian high, and clear sky or a thin mid to high level cloud deck. Also light winds, like I said before, and a deep mixing layer. When these features are occurring, we must next look at the conditions at the top of the boundary layer. So here's kind of a skew T to kind of show. So we have the very dry air, around 800 millibars, and the key is in the boundary layer where there is more humid air, and there's also weak inversion happening as well. So the very dry air mixes down towards the surface, and then there's that weak or no inversion. So there's no real cap on it. So when these weather patterns set up, it allows for the air to mix all the way down to the surface. And like I said, it's difficult for models to pick up on this. It's kind of, once you see them happening, you have to react to it. That's what kind of what we had thought as we were coming to the end of our time doing this research during my volunteership. So the very dry air at or just above this boundary layer usually was between 1 to 2 kilometers or 3,000, 6,000 feet. The minimum cap or inversion at the top of the boundary layer, and then the boundary layer becomes very well mixed with surface dew points, and RH can drop rapidly then. So these dew point bombs tend to be focused over small areas, usually a stripe just a couple of counties wide. It seemed like the type 1, so the building high pressure events tend to be more localized, while type 2, which is the approaching warm front events, tend to be more geographically widespread. So we looked at 2 scenarios here. The blue line with the drop of 5 degrees, the rise of 5 degrees, and then the red line was 10 degrees and 5 degrees. So the red line obviously was more rare than the blue line was. And then it seemed like the dew point bombs most often occurred across these northern counties to the east as well, and then least often in the southwest counties. I'm kind of going to skip ahead here because I am running out of time. So like the last thoughts that we had is that even if the dew point bombs don't develop, knowing our tendency to high error and the relative humidity forecast for these weather situations will improve the forecast over time. So so this gives us more time to highlight the potential for these lower RHs in the fire weather and spot forecast discussions. So the future plans for NWS, from what I last know, is that we were going to implement these ideas and become more aware of the weather patterns, and then also to mention the potential for these lower RHs in our fire weather forecasts. So that's all I have. Any questions from you all?
Yeah, I have a quick question. So when you were verifying these observations against forecasts, were these forecasts issued by NWS, or were these raw forecasts like directly from a model like the HER or the NAM or something like that?
These were directly from the National Weather Service office in State College.
Okay. Good. Yeah. I was kind of, part of me was curious to see if maybe different models had different biases depending on, for instance, what the boundary layer scheme was that they were using within the models.
Yeah, absolutely. We kind of dabbled with looking at the high res forecasting models for that reason. But unfortunately, I think I was only there for like 6 months, so we can only do so much. But
I know
Thank
sitting
you.
there, we had access to a certain number of models in the GFE.
Mhm.
Sometimes none of them fit what was actually happening. So it was, always a task to manually try to fix things. But so,
Yeah.
even though it's our forecast, there's probably a model that was underlying that, whether it was manipulated or not, depends on the forecaster and the situation probably.
Mhm. Yeah, I think Rob had mentioned that it was kind of difficult to find the data that we needed at certain points in time, especially when we were looking for model data. So
Nicole, I have a question.
yes.
That was interesting, by the way. I wonder if, and maybe you already looked at this, but one parameter that might have some predictive capability would be something called the convective temperature.
Mhm.
I don't even know if we still teach that anymore. I teach that when I teach mesoscale, but I'm not sure it's widely taught in thermodynamics anymore. It's basically the temperature at which, given the surface dew point or mixing ratio, it's the surface temperature you need to reach to have no surface-based convective inhibition.
Yeah.
And it's really a misleading term because it's often thought that once you hit the convective temperature, then that's when you get convection. And generally speaking, you probably don't want to hit the convective temperature for the worst thunderstorms. That's a whole nother story. But in this application, if you get close to the convective temperature, what it means is that there's nothing impeding dry air aloft from mixing down. Once you hit the convective temperature, boom, all of a sudden you go from maybe a kilometer of deep mixing to it could jump to 2 kilometers in a matter of minutes. And so I don't know if that's something that might be worth looking at. I have no doubt that the models wouldn't handle this well because the mixing's being done in real life by turbulent eddies, and those are not resolved in a model. It's got to be parameterized mixing in the model, so it's just not going to be reality.
Yeah, exactly. And like I feel like something like that would be very prudent for areas that are very susceptible to wildfires and stuff like that. Not central Pennsylvania, but but when we would do like control burns and stuff like that. But yeah, like I'll mention that to Rob and see if he had done anything about that parameter. Thank you so much for that information though, Paul.
So I'm curious, did you ever like look at why some areas were like the forecasts were more off than they were in other areas? And like, because I know you were looking at Brian was really interested in Williamsport. Was there ever any reason found for why Williamsport was so off? Or
I want to say that it's based on its geography and based off of the local landscape with the mountains off to their north, and then it's the way that the city and the ASOS was situated was unique to the other ASOSs. We did do other research for other ASOS sites, like in State College and other sites as well across the CTP, but it seemed like it happened in Williamsport the most, and I feel like we don't quite also understand why it happened in Williamsport so much, but it also happened in State College too on multiple occasions. And we do have graphs and stuff on that, but I mean we couldn't fit in our presentation, unfortunately. But yeah, I think it has to do something with their geography and with the way that those weather patterns had situated. So. I hope that answered your question.
Yeah, thanks.
Yep.
Thanks, Nikki. We'll move on to the next presentation, and Christy will introduce our speaker.
All right. One. There we go.
All right, going to introduce Chris Long here. Chris is a senior at Penn State, double majoring in meteorology and geography. When he first arrived at Penn State from his home in central North Carolina, he was just a meteorology major. However, after stumbling upon GIS in his freshman year, Chris decided to pursue a minor in GIS, and then when the opportunity presented itself, he added the second major. His main interests, however, lie in the crosshairs of the two disciplines. He is particularly interested in the social sciences aspect of meteorology, especially in understanding people and places that are at risk of being affected by adverse weather. Last summer, he was the William N. LaPenta intern at the NWS Weather Prediction Center, where he did verification work on the Winter Storm Severity Index. Then this past fall, he was a virtual student volunteer here in State College at the NWS office, where he worked to identify populations in central PA vulnerable to severe weather. After graduation, Chris plans to go to grad school for geography. He's currently crossing his fingers for an acceptance, and we hope so as well for you, Chris. So I'll turn it over to Chris. He'll be talking about severe weather vulnerability in central PA.
Yeah, thank you. And there has been good news. There have been a few acceptances since that was written up, so this is exciting. I will go ahead and share my screen here. So I'll be presenting on some of the work that I did as a volunteer this past fall at the NWS State College. And so this is titled the Severe Weather Vulnerability Project. It's been going on. This was predated to before I was a volunteer there, but then I kind of picked it up and move forward. So I'll start with a little bit about what our goals were for the project. So we wanted to develop visualization, and we wanted to determine potentially vulnerable populations in the central Pennsylvania region. And we defined vulnerable as communities that were more at risk of severe weather due to technological, physical, or economical limitations. And so that included, but was not limited to, examples of like the Amish, people that may be deaf, blind, or visually impaired, mobile home parks, etc. And so then what I did was I sort of brainstormed and expanded the list of these vulnerable populations. And then I went a step further and helped to create visualizations so that NWS forecasters and emergency managers have spatial awareness of these groups in the event that severe weather does occur. So we started the project back in September, and we looked at what's already in AWIPS because it wouldn't have been any help if I was finding data that was already available. So this was what was in AWIPS before my project started. So we had school districts, but not points. So I think we just had polygons of the outlines of school districts. We had dams, we had colleges, points of colleges and universities. We had points of amusement parks, ski resorts, power plants and factories, solar farms, and wind farm turbines. All of these areas were determined that they were at a little bit of a higher risk of severe weather. Say if you're at, well, a ski resort isn't a very good example, but if you're stuck there in severe weather, you may be without help in the case that does happen. So then I went through and kind of throughout the fall semester, I went looking for new data, and I went looking for it in a few different places. The first one that I found, this was super easy because it was data that was already put together, and I didn't really have to do much other than take the data in and snip it to the central PA county warning area. And this was data from the Homeland Infrastructure Foundation level data, which is done by the federal government. And this included National Park Service land, locations of nursing homes, locations of mobile homes, and finally public school locations. So we went a little bit further than just the outline of the school districts. Now we actually had locations of each public school. Obviously during severe weather, not the greatest place to be, and we want to be spatially aware of where public schools are when we do have severe weather coming through. But then I also had to create a few of my own data sets. This was a lot more time consuming, especially the fairgrounds and the campgrounds. I had to go on all sorts of weird websites, and I tried to find as many fairgrounds and as many campgrounds in the county warning area as possible, and I put them all on a map. This map right here is just an example of, those are all of the, I think those are campgrounds in central PA. And so I put them all into my own sort of Google map, and then I made it into a KMZ, and I was able to get it into ARC that way. And then finally, there were a couple other data sets that weren't from the federal government, but I also didn't have to make them myself. Again, these were mostly just data sets where I was able to just snip it to the county warning area. And those included from Esri, golf courses and park districts were already in Esri. So I was able to quickly get them up in the ARC area. We actually had a data set from Andy Wilson, who did a study on Amish populations a couple of years ago. And that's actually what that map is in the bottom right corner there. That was kind of neat to work with. And then finally, we had some state park data from the PA DCNR, and I was able to quickly pull that in as well. And so when you put that all together, this is what it looked like, which isn't that much help, but spatially you can kind of see where a lot of things are clumped. Not very surprisingly, a lot of these vulnerable areas were in the population centers, especially down in the southeastern portion of the CWA, York, Harrisburg, Lancaster, but you can also see near State College as well, a fair amount, where you have the population centers, you kind of have the more vulnerable areas. But then to make it better for the weather forecasters, I was able to put each of those different icons was to a different data set. And so I was able to put those all into zip files. And so that way we can hopefully get them into AWIPs. And so that way they can be, on the system as severe weather is occurring. And so the forecasters can be aware of those and maybe reach out to emergency managers or people like that if there are folks in the line of danger. And so at this point, I want to thank everybody at the Weather Service who made this possible, and also others who helped along the way. And I'm going to move over to a different tab here now. So this is actually the map in and itself. I wanted to kind of point out some specific things, if my computer will cooperate here. I guess there's a lot of data on here, so my computer isn't being very cooperative. But just to kind of give you guys a little bit more of an in-depth view, you can see, I think a lot of what shows up on this is the Amish populations. So that's these bright orange colors here. So if I turn that off, if I can, there we go. If I can find that, you can see sort of the other vulnerability area or vulnerable areas that are located on this map. But there's I think we often don't worry as much about vulnerability in areas like central Pennsylvania because there aren't many big cities here. You don't think about, if you don't have a population center, you think that there's not much to worry about. But in reality, there's a lot of rural areas, there's a lot of campgrounds, and Pennsylvania does have a fairly old population in comparison to other areas. So there are quite a few nursing homes in the area. And so just being aware of where these locations are and what locations might be most vulnerable to severe weather is a really good tool to have in our toolbox, so that we're making sure that we can keep as many people safe in times of severe weather. So if you guys have any questions, I can take that. I can also, if you want to see specific layers on this map, I can show you those as well. So just let me know. Oh, I'm sorry. If my audio cut out, sometimes my Wi-Fi does that, but.
No, it was me, Chris.
Oh, okay.
Hey, Chris, good talk. This is really interesting stuff. And yeah, I kind of alluded to some stuff like this in my own talk about considering, how threats might change and how you might change tornado warning forecasts because of that. So this is really intriguing work from our perspective. I guess I'm curious how much of the points on this graph, and maybe you showed it, did you say you had to come up with and draw, and how much of this was just is packaged and ready to go from other data sets?
Right. So if I can kind of go back to here. So there were some really good data sets. So nursing homes, mobile homes, and public school locations all came from this Homeland Infrastructure Foundation level data. And that is, as far as I know, it's at least CONUS wide, because when I downloaded the data, it took forever because it's a pretty massive data set. But yeah, you can certainly get this CONUS wide. And I think all of these, with the exception of, well, the top two, golf courses and park districts from Esri, I believe those were CONUS wide as well. And so those would be really good to be able to pull out and use for, whatever you need to use them for. I didn't know they existed until I kind of was poking around, but they're pretty neat to play with. Yeah.
Thanks.
I'm kind of curious if you reached out to, say, Pima at any point, just due to the fact that I'm sure they have some GIS specialists there that keep track of some of this stuff. And I'm just curious if they have shape files or if they could benefit from this information as well.
Yeah, it's interesting you say that, because we actually, we started the internship way back in like the early part of the fall semester, talking to a professor, Dr. Jack Freeman, who I think he's at Oklahoma, and he did a project where they did something similar to this, except they basically pulled, it was one of the Weather Service offices in the deep south. I think it might have been maybe Birmingham. It was one of the Alabama offices, I think. But they went to the emergency managers and they kind of had them do their own sort of mapping. And so that's actually not something that we did throughout the course of this project, but I think that's definitely something that could happen in the future, because especially when you go down to like county-wide emergency managers, they might have a better idea of the specific areas that might be vulnerable in their county, or they might even define vulnerable populations as something different than we do, just because they have that better understanding of their specific local area. So that's definitely something that we could do in the future. And as far as, giving this to Pima, I would certainly be open to that. But no, that's not something that we've done so far, at least. But we can definitely, try to do that.
And just curious, is that publicly available, that vulnerabilities URL?
I believe it is. Yeah, I can get a link to that if you want it.
Sure.
I'm pretty sure I made it public. If not, I can make it public.
Cool. All right, and I will introduce Jacob. So Jacob Morse is a senior honors meteorology student at Penn State University, focusing on weather forecasting and communication, as he plans to get a job in broadcast meteorology after graduation. Jacob is a NOAA Hauling Scholar, and throughout the summer of 2020, he worked with the National Weather Service in Bismarck, North Dakota, to research better messaging strategies for winter storms. He took a social science research approach to the topic as he tried to figure out the best way to incorporate uncertainty and probabilistic information into winter weather forecasts. He is continuing to work on this research at Penn State for his senior honors thesis this semester. Jacob was also the 2020 head of communications for the Campus Weather Service, is currently the vice president of the Penn State branch of the AMS, and is a part-time forecaster and host on Weather World. So his talk will be evaluating the usefulness and response to uncertainty-driven and probabilistic hazardous winter weather messaging. Feel free to go ahead, Jacob.
Awesome. Thanks for that introduction. Can everyone see my screen right now?
Yep.
Awesome. All right, so kind of got a lot to cover here because this is kind of turning into more of a long-term research project now that started over the summer with the Holling Scholarship, and now I'm continuing it for my honors thesis. So like was mentioned, this is kind of a social science-based research project and looking specifically on winter storms and how they're messaged by National Weather Service offices in the long term, kind of days 4 through 7 before a winter storm, medium range, days 2 through 3 before a storm, and also short range when snow maps are being released. And how can we kind of incorporate uncertainty information at all of these lead times, as well as how can we best use graphics to communicate forecast information at all of these lead times before a winter storm. So the overall goal is to improve winter weather messaging and to achieve more consistency from Weather Service office to office across the country when messaging winter storms. So I kind of gathered a bunch of graphics that Weather Service offices used all across the country during the winter season on social media. I organized all of these graphics and identified some of the key differences between them. I also used some social media analytics to study specific large snowstorms that impacted some parts of the country. And then I received feedback with a couple of surveys with non-meteorologists as well as with some forecasters. And then I conducted some focus groups with broadcast meteorologists in North Dakota and emergency managers in North Dakota as well. So first we'll start off with looking at those long range graphics, kind of days 4 through 7 before a winter storm is approaching an area. And there's some common graphic types that are used by Weather Service offices. One is using kind of a broad brush circling some area that has a potential for snowfall. Another one is also doing a similar thing to that, but also incorporating some sort of timing information into the graphic when the storm will be at certain points. More of a generalized when the storm is expected to impact the area with a list of dates or a timeline of the storm. And then more of a kind of text-based graphic, what we know, what is uncertain, what we don't know, stuff like that. So from those initial survey results over the summer with North Dakota non-meteorologists and North Dakota forecasters, most people preferred having this kind of circled area graphic at this lead time, but there was a lot of differences. Some people preferred other graphics over others, so there's no hard and fast rule with these graphics. I think it's the overall theme should be that these graphics need to be kept simple, and also using some kind of map visual at this lead time is a good practice. With the risk probability graphics, so now going more into days 2 to 3 before a winter storm, some Weather Service offices use these risk probability graphics. They're also called probability of exceedance graphics, and they're kind of a good bridge to use between those long range graphics and before a snow map can be released. So these are created when the WPC Super Ensemble is run, and you get this distribution of values of snowfall amounts that are predicted for a certain area. And that distribution gets shifted by forecasts that the WPC puts out, as well as forecasts that each Weather Service office puts out. So that ensemble distribution of what the snowfall amount is looking like for a certain area gets plotted, and it's plotted on these probability of exceedance graphics as a threshold value. So the probability of exceeding a certain snowfall amount, such as 4 inches, 6 inches, etc. Some Weather Service offices simplify that graphic on the left a little bit further into 3 categories for easier interpretation. So we'll go into some differences among these graphics. First, something about the purpose of these graphics. Why are they used? So they're a good tool to use when there's too much uncertainty for those snow maps to be released. They do a good job of communicating kind of the spatial coverage, where's the greatest impact from the storm going to be, as well as the likelihood of the storm. And it allows people to prepare for that storm and change travel plans at this lead time. And there's also some uncertainty information that's conveyed inherently with these graphics because it shows people what that probability is of exceeding a certain snowfall amount. So some of those differences that one Weather Service office might use with this style of graphic versus another is with the color gradient. So I showed you one of those yellow, orange, and red color gradient graphics for the risk prob style graphics. Also, some offices just leave it as that blue shadings with some probability percentages at each point location. Other offices have a different style, a different color scheme. And then this is more of a style that you'll see the WPC put out a lot of times on social media, but but a lot of this is pretty much the same information that's being put out with a different color scheme. When I surveyed the forecasters, about 50% preferred this color scheme for this style of graphic. And the emergency manager and the broadcast meteorologist in North Dakota also preferred this color scheme, but it's should be noted that these people are used to using this style of graphic before, so there's some bias with that. There's another difference that these graphics present. Some offices include those probability percentages within their color scale, as well as at each point location. Other offices just leave it more generalized with these graphics as low, medium, and high categories, and not having that probabilistic information kind of standing out on the graphics. 60% of the forecasters we surveyed over the summer in North Dakota liked those percentages on the color scale. And there's been some past social science studies that have shown that people make better decisions when they have those probabilistic percentages. It makes the forecast less ambiguous, less open for interpretation from person to person. And then the emergency managers and the broadcast meteorologists also agreed with this differentiation between those style of graphics. This style of graphic can also be used to communicate other hazards. Forecasters that we surveyed would be willing to use it to communicate icing or freezing rain potential, to communicate travel impacts, communicate blowing and drifting snow, and possibly wind chills as well. So this style of graphic with these 3-tiered color schemes can be used for a wide variety of applications. So kind of one of the key takeaways from looking at these risk probability graphics is that I believe that they're well understood and they're useful to communicate that uncertainty in the impact area of a winter storm before those snow maps can be released. But some more standardized graphic style needs to be adopted to improve the consistency across the National Weather Service. So now we're going into the final kind of category when we're only 1 or 2 days before a snowfall event and snow maps are starting to be released. Uncertainty can still be present at this lead time, and it's often the case when there's a very tight gradient in snowfall amounts, or if models are widely skewed one versus another. So there could be a lot of uncertainty in a certain region of a snowfall map, and some offices circle that greatest area of uncertainty and point it out on the snow map. And some of the non-meteorologists that we surveyed, a majority of them said that if they lived in that circled area, they would check back for the forecast updates to see if anything changed, and they were prepare for higher snowfall amounts in case that forecast changes. So it changes their actions a little bit and gives them more information when that uncertainty is called out on the snow map. The feedback was also very positive when we talked to emergency managers and broadcast meteorologists about this circled area of uncertainty. And it's important to do this on the first snow map that's released, just because with some of the social media research that I did, that first snow map that's put out on Twitter or Facebook gets a whole lot more attention than some of the subsequent snowfall maps that are released from National Weather Service offices. So I think that this practice, when it's necessary, should be done by more weather forecast offices because of the overwhelmingly positive reviews that we've gotten. So this was kind of phase 1 of the research, what I did over the summer with that relatively small sample size of a survey with non-meteorologists in North Dakota, as well as forecasters in the central region of the National Weather Service. And I've been continuing this with a much larger survey size now for my honors thesis in this phase of the research. I also wanted to touch on how some of this research is being implemented with the Bismarck office, which I worked with hand in hand over the summer. And they have somewhat of a winter weather messaging funnel that they use that's very similar to what I just talked about with the different lead times, days 4 through 7, days 2 to 3, and then days 1 to 2. So long range, medium range, short range. So with the long range, they're using this sort of template this winter, where they have some of that, what we know, what is uncertain information, and then a map that shows where the threat of the winter storm or the threat of the highest accumulations is most likely. So it combines some of that information that we were talking about that people liked with the long range winter weather graphics. So now looking at what they're using more so for the medium range style of communicating winter storms, those risk probability graphics and that color scheme is well established. The North Dakota offices were one of the first to use these style of graphics, so they're going to continue to do that and expand them to use for other hazards, such as for freezing rain. So they're going to use this template for freezing rain potential. It gives the chance for greater than 1/100th of an inch of ice accumulation, because ice accretions are pretty rare in North Dakota. But using this color scheme for freezing rain is something that the Bismarck office is going to be doing more this winter. And then for those kind of short range graphics, they're going to continue to incorporate that uncertainty information on snow maps when it's necessary. And they're going to start to experiment with different snowfall ranges. So usually there's just set bins for snowfall ranges on these snow maps, like 3 to 4 inches or 4 to 6 inches, 6 to 8 inches, etc. You can also use more probabilistic information for these snowfall ranges with 25th and 75th percentiles of that distribution as your snowfall ranges, as that bottom and top number. This gives a little bit of a wider snowfall range, so you got to be a little bit careful with that. But incorporating more probabilistic information could be helpful and allow more of these forecasts to verify, give more accurate forecasts at the end of the day. Now with the State College office, I got in contact with them after presenting the results of this research from over the summer. And they created a new winter weather outlook graphic for days 4 through 7 as a lead time, days 4 through 7 as a lead time before winter storm. So it has the same color scheme as we saw with some of those risk probability graphics in the past. And it's based on the Weather Prediction Center's days 4 through 7 probability of exceeding 1/4 of an inch of liquid equivalent of snow or sleet. So using the words plowable snowfall allows for a little bit of interpretation from person to person. But if it's 10-to-1 ratios, that's generally 2 to 3 inches of snowfall if there's no sleet mixing in as well. So these have been released throughout this winter. They've been used for several winter storms so far. And I think they've been working out pretty well for using that long range information and adding another graphic to their toolkit to message winter storms at this long range lead time. So now with that new survey that I was kind of hinting at, that's been distributed. We've gotten a bunch more responses than I had with that survey over the summer, and a lot more of the public side of things as well. So with that plowable snowfall graphic, with this initial results of this survey, people are saying that 3 to 4 inches is what they consider plowable snowfall. So people are interpreting this in somewhat of the right sense with saying that 3 to 4 inches is what they expect to see if they're in the high category, for instance, of this probability of plowable snowfall graphic. There was some talk about, is that term too vague, or does it need to be kind of pinned down to certain snowfall amounts or not? So this is just some more information that could be valuable for the Weather Service. There's another part of the survey where I asked people about the different color schemes of those risk probability graphics that we talked about earlier. And one of the key takeaways from these kind of initial results is that I think people prefer having that additional probabilistic information on the graphic. They understand it, they can interpret it, and with the 2 highest color scheme preferences coming with those discrete percentages plotted at each location. So that's interesting as kind of like initial result from the survey. And then one of the big parts of the survey is where I placed respondents into each of these 4 different scenarios. So they get one of these scenarios from a different part of the country where 4 graphics are given to them. And these are graphics that were actually used to communicate a winter storm. And I asked them questions about each one of these graphics. But the thing is that each of the graphics is different from scenario to scenario. So we can do some comparing and contrasting to see if people prefer certain graphics at certain lead times over another. There's a whole lot to kind of parse out from the results from this second survey that I'm doing. So all this is kind of going to be included with the honors thesis that I'm writing right now, but I'll take any questions that you guys have at this point.
Jacob, this is really cool, and appreciate you incorporating us in the midst of it. Really happy to see the high response rate that you've had so far. And I'm particularly intrigued by the plowable snowfall being presumably fairly accurately understood by the public. We kind of hemmed and hawed because maybe you mentioned this, but basically that's like a probability of liquid equivalent greater than 1/4 inch. And so with snow to liquid ratios, that can be anywhere from like 1 inch of snow to 6 inches of snow. So it's good to hear that people are more or less in the ballpark. Curious, kind of big picture from your survey results that you've looked at thus far, are there any surprises that you've kind of encountered that were maybe contradictory to what you expected the public to respond in?
Yeah, I think one of the big takeaways is that people want the confidence or uncertainty information. So I asked people to kind of rank what types of forecast information you think is most important before a winter storm. So snow totals were one of the top choices, but amount of confidence in the forecast or amount of uncertainty in the forecast was ranked really high up there as well. So I think people want to know how confident or uncertain that a forecast is. And then I think people interpret uncertainty and probabilistic information better than we might think because of the types of graphics that they're choosing as their preferences. So like having percentages of like 70% chance of exceeding 6 inches of snow, having that 70% plotted on the graphic itself is preferred by a lot of people so far.
Hey, Jacob, did you actually do anything or look into, you talk about people, a large percentage of people who see the forecast are the people, not necessarily the decision makers.
Right.
And I know we always take it, whenever we have a forecast for anything, we're always being second guessed or criticized because we didn't quite get it right. But how much of that did you look at?
You talking about with like emergency
General
managers and partners?
General
or?
General public.
Oh, okay. Yeah, no, I haven't really looked at like the response after a winter storm, someone's feedback about how incorrect or correct a forecast is. One thing though, one of the questions on the survey is about those 25th, 75th percentile snowfall ranges and using wider snowfall ranges on a snow map. So instead of using a 4 to 6 inch snowfall range, having a 2 to 9 inch snowfall range that's based on probabilistic information when creating that range. And that range is going to verify a higher percentage of the time. And it was interesting to see.
It's also next to worthless.
Right, exactly. So
yeah.
People's feedback of that has been interesting to see.
Yeah. I judge everything by how I can explain this to my wife.
Right. So some information might not be necessary with this. Like, there's a fine line between too much statistics, I guess, with the forecast.
I think some people still want words, is what I'm trying to say. Showing, the general public a map with a lot of colors on it. I don't know. I'm retired now, but I'm just not sure of the utility of that yet. People still want to be told it's going to snow, how much, and then they want to hold your feet to the fire if you tell them 6 inches and they only got 3.
Right.
Maybe that's the nature.
Yeah, I think something that could be brought up though is how much a forecast changes. So like if you put out a forecast for like 6 to 8 inches, but the next snow map only says 2 to 4 inches, how is someone going to react to that?
Yeah, what do they actually remember? And we also found that you say 4 to 6 inches, they hear 6.
Right.
You say 4 to 8 inches, they hear 8. So
yep.
So kind of building off of John's question, I'd be curious to see if anyone's gone through and done some past validation on some of these, especially risk maps out several days to see how close did that get to the actual extent of the forecast. And when you forecast something as a high risk, is your hit rate on that like 80% of the time you're actually hitting the area that's high risk or not? That's communicating uncertainty. I have the same issue with John. I'm working with farmers and people who are marketing products to farmers, and when we want to communicate uncertainty, they don't want uncertainty. They want to know whether it's going to rain, and they want to know when it's going to rain. and they don't, our ranges and our percentages don't resonate with them. So that's this kind of messaging issue and how we communicate risk and uncertainty has been a big issue with us. So I'm happy to see that you're doing the social side of the research, but we found that sometimes communicating that when we say high risk, we're hitting a high risk area 70% of the time. That actually resonated more with our farmers and our marketers, more than just saying, just trust us when we say high risk. So, but I don't, it's our farmers are still probably more weather sophisticated than the general public too. So it's still a challenge, with all this.
Yeah, I definitely think that some people understand that there's inherent uncertainty to every forecast, whereas other people don't believe that. They want more of that deterministic option. So yeah, it's interesting to kind of parse through all that information. What talking about the verification though, there's been some work done, at least in the central region, that I looked at with the probability of exceedance graphics and how those have been verifying. I haven't gone into the weeds too much on that just because I've been so focused on the survey and social science side of things, but there has been some work on the verification of those probability of exceedance graphics.
Yeah, another thing we found years ago, we were very surprised. Even though we may have conveyed a high degree of certainty in certain forecast situations, say a big snowstorm coming, decision makers are different on every level. And we found that actually, like the trucking industry, instead of staying home or taking that information and saying, well, maybe we should err on the side of caution, they actually go the opposite way. They'll try to beat the storm and they're willing to almost drive into it because they've got their deadlines and all these different criteria they've got to use. So we were a little surprised that even though we're telling them some good information and forecasts were good, it sounded almost like they weren't listening. They were going to go anyway.
Yeah.
So that's another layer of decision making. This may be layered below EMAs and so forth.
Yeah, you can't control people's actions. You can only tell them what you think is going to happen.
Yeah, I did that for years, briefing pilots. I can only offer advice if they still wanted to fly.
All right, I guess we'll move on to our next speaker. This is Pete Young, by the way, and that's going to be Callan Parker. And the title of her presentation is Creating and Exploring a Climatology of SPC Watch Products. And a little bit of her background. Callan is currently a senior meteorology student at Penn State with interests in severe and tropical weather. Throughout the summer of 2020, she virtually interned for the Storm Prediction Center as part of the NOAA Holling Scholarship Program. During the internship, she worked with her mentor, Dr. Berkeley Gallo, to investigate a climatology of severe thunderstorm and tornado watches across the CONUS. Last fall, she was given the opportunity to volunteer with the National Weather Service in State College, where she further was able to develop skills in computer coding and forecasting. Following graduation in May, she hopes to use these skills to attend graduate school to obtain a master's degree in meteorology and then work for the National Weather Service. So take it away, Callan.
All right, can you see my screen and hear
Yep.
me? Okay.
Yep.
All right, so as mentioned, we're going to be taking a look at a climatology of SPC watch products, which I worked on this past summer with the Storm Prediction Center for my Holling Scholarship. So our objective with this project was to evaluate how severe thunderstorm and tornado watches have evolved from 1970 to 2019 by meteorological season and region in terms of number of watches, watch size, watch duration, and then different verification statistics such as prevent, verified, and probability of detection. And our goal with this was to provide insight on both the evolution of severe weather and our ability to forecast severe weather threats over time. For some background, convective watches are issued by the SPC when conditions are favorable for multiple events of organized severe convection. So for a tornado watch, this would be if 2 tornadoes or 1 EF2 or stronger tornado is expected. And for a severe thunderstorm watch, this is if at least 6 events of severe hail or severe wind are expected. And this should be for a region of at least 8,000 square miles for at least 2 hours. In the early 2000s, watches transitioned from having a parallelogram extent to a county-based extent with an accompanying parallelogram. And for this study, we're only concerned with the parallelogram extent of the watches. The watch data set used was provided by Andy Dean at the SPC, and it includes all available watch data from 1/1/1970 to 6/1/2019. And then the reports data set used for the verification comes from the SPC WCM page, and it includes all available storm data, tornado, hail, and wind reports from 1/1/1950 to 12/31/2018. To split watches by region, we chose 6 regions, being the West, the Northern Plains, the Great Plains, the Midwest, the South, and the Northeast. And these regions were chosen for having similar environments and storm climatologies. And then for the watches that fall on the border of 2 or more regions, they're simply just sorted into the region in which it has the most overlapping area. So this watch would go into the green area here. To split watches by season, this was based on meteorological seasons, and it was sorted by the start date of the watch. And then for verification statistics, this has only been looked at for tornado watches so far, but they include percent verified or PV, which is equal to the watches that contain a report divided by the total number of watches, and probability of detection or POD, which is equal to the number of tornadoes in watches divided by the total number of tornado reports. And these are both evaluated on yearly time scales. So we can get started by some results. Here we have maps of watch count by decade, thunderstorms. And you'll see as I step forward in time, the count generally rose from the 70s to the 80s, and then again into the 90s, and then somewhat steadied out into the 2000s, with most areas again staying steady or decreasing, you'll see, other than the Northern Plains, which sees a slight increase. And then as we go into the 2010s, there's really a decrease kind of across the board. But what's interesting here is you'll notice that no matter which decade we're in, the maximum here kind of remains over the Great Plains. That's not totally the case, you'll see, if we jump to tornado watches. You'll notice immediately in the 70s, we have 2 separate maximums, one in the South and one in the Great Plains. And as you step forward in time, you start to see these regions merge into one by the 80s, and then it truly is one big region by the 90s. You also notice the count went up here pretty much everywhere. And then as we step into the 2000s, count starts to decrease again, and then even farther into the 2010s. Something else you'll notice is that these last 2 decades, the maximum really starts to occur only over the South and disappear over the Great Plains, right here. So we can take a look at this graphically too. On the left, you can see the surge in severe thunderstorm count was observable across all regions. And then again, too, you can see the rise that we saw in tornado watch count. And this is mostly due to an increase across the South and the Great Plains. Something you couldn't necessarily see from the maps was this secondary maximum that we see in tornado watches in the 2000s. We just think given the time of this increase, it may have to do with a better understanding of high shear, low cape environments, especially because this lump is prominent across the South, where you would find those environments most often. Something else you can see if you compare these side by side, it's kind of hard to tell, but tornado watch count outnumbered severe thunderstorm watch count in the Great Plains at the start of our time frame, and then that started occurring in the South towards the end of our time frame. And that's unique to both of these regions to ever have years where tornado watches actually outnumbered severe thunderstorm watches. We can also break down count by season. So here we have severe thunderstorm count. And again, you can see this rise throughout the 80s is present across every single season. especially across the Great Plains in the south, which continues into the fall and the winter. And something else that you will notice here that, again, you couldn't see before we broke it down, but we have this secondary peak in severe thunderstorm watches during the summer in the 2000s, and that doesn't show up in any of the other seasons. And this can only be seen across 3 of the regions, mainly the Great Plains, the South, and the Midwest. So that was something interesting. We can also take a look at tornado watch count by season. You'll see that these graphs don't look as similar as each of the severe thunderstorm watches did. They kind of all have their own trends. But one thing you'll see too, again, is we have this increase throughout the 80s across all of them. You'll notice that trends in the fall and the winter are almost entirely determined by trends across the South, which again, shouldn't be too surprising climatologically speaking. Another interesting takeaway I took from this is that you'll notice at the end of our time frame, at least in the last 2 decades, is that tornado watches are now outnumbering tornado watches in the South are outnumbering tornado watches in the Great Plains in 3 of our 4 seasons. The only season that that's not true in anymore is during the summertime, where you can see the South is down here and the Great Plains are right there. We can also take a look at watch size. And the first thing that sticks out here is that tornado watches have been consistently larger than severe thunderstorm watches throughout our time frame. And also both watch types saw a peak in the 70s before falling off throughout the late 70s and 80s. We think that this decrease in size may have to do with improvements in forecasting due to advancements in satellites and stuff like that. And then they both somewhat steadied out before another recent fall off in the last few decades, which we think may have to do with the new county-based warning method. We can look at watch size by region. I don't have them shown here, but the trends for the South, the Northern Plains, the Great Plains, and the Midwest all really closely mimic CONUS. So it seems like these might, again, not have to do with changes in the weather itself, but with how exactly we're drawing the watches. But for the Northeast and for the West, trends aren't exactly the same. You'll notice here for the Northeast, we see the secondary peak in size in severe thunderstorm watches into the late 90s and 2000s. Not sure if this has to do with storm mode, maybe because we have so many squalls here, we're drawing larger boxes. And then you'll notice in the West that both severe thunderstorm and tornado watch size has been increasing throughout pretty much the whole time frame. And the sample size for tornado watches is fairly small here, so I wouldn't put too much merit in that. But again, maybe this most recent increase could have to do with that county-based warning method, just because counties out there are so large. That could have something to do with the most recent increase we've seen. We can also plot watch size with box and whisker plots by year. And the biggest takeaway that you can get from these plots is that you'll notice that trends across both of them are pretty similar and that variability has just been increasing in time. You see, we have these really small whiskers to start in the 70s, and they just gradually get bigger as time goes on, with more and more outliers appearing for both. And we think that might just have to do with, again, better forecasting. Maybe your forecasters are better drawing a watch box to fit a specific event rather than just drawing a standard size and leaving it at that. So with that, both watch types have had their largest and smallest watches in the last 15 years, and this trend is consistent across all regions. We can also take a look at duration by season and by region, and something interesting is that the mean duration for both watch types falls between 5 and 6 hours for all seasons and for all regions. Something else that's interesting is that tornado watches are more likely to have long duration outliers than severe thunderstorm watches. You'll see we have like quite a few up into this 11, 12, 13 hour range, and they don't really show up for severe thunderstorm watches. They're especially apparent in the South and in the Great Plains and in the summer and fall. So we think that this could have to do with tropical systems. Of course, that's not going to be what it is entirely, because we do have some in the spring, but that definitely could be a factor in where we're seeing them and what time of the year we're seeing those long duration outliers. We can also look at duration by year. And again, this is just kind of to look at the trends. And you'll notice that these plots look very similar between severe thunderstorm watches and tornado watches, again, with a lot of variability to start, which generally decreases throughout the 70s. And then we kind of have this stagnant period throughout the 80s and the 90s before both see this jump in duration around 2005. And that mostly has to do with an increase in the long duration outliers. And again, they're not here, but these trends look pretty much exactly the same across all regions. So that means that they're probably the result of some sort of policy changes going on at the SPC or something like that, rather than actual changes in the weather. And then lastly, we can take a look at the verification statistics for tornado watches for CONUS. And here you'll see that percent verified has generally been increasing with time. And again, what this is the watches that contain a report divided by the total number of watches. So what this means is that it generally means our forecasting skill has increased, which is what we want. So that's pretty good. And then POD was generally increasing for much of the time frame before it started to decrease around 2011-ish. And again, what POD is the reports within a watch divided by the total number of reports that year. And we think that the recent decrease may be linked to just having very few tornado outbreaks in the most recent years, because that has been linked to a reduction in annual POD. So in summary, watch count saw a surge for both types throughout the 80s and 90s. And since then, trends have been more variable seasonally and regionally. Trends in watch size are consistent across most regions other than the West and the Northeast. And tornado watches also tend to be larger than severe thunderstorm watches in all regions other than the West and the Northeast. Watch duration has been much more variable with time than it is across different seasons and regions, and recent reductions in POD for tornado watches may be linked to less high-end events. So from here, we want to look at how PV and POD have changed by season and geographic regions, and of course, evaluate these for severe thunderstorm watches. We also want to explore the evolution of other parameters, such as the start time of watches by season and region and watch probabilities. Lastly, I'm going to give another thank you to my mentors and then others at the SPC for helping me out. And that's all I have. So if you have any questions, you can ask me right now or email me. Okay.
Hey, Callan, this is Pete Young.
Okay.
Maybe more of a comment than a question, but the increase in the number of watches dramatically in the 80s and 90s. Did you look at all about, that was the introduction to Doppler weather radars?
Yeah, we had talked about that. Yeah, we think that definitely has a lot to do with it.
Yeah, there was a huge effort to kind of redouble the Weather Service's efforts in verification of warnings during the rollout of the Doppler. So I think there was a much more aggressive kind of beating the bushes, trying to find severe weather reports. So that might kind of be a feedback mechanism there that happened in the 80s and 90s.
That was interesting. I'm looking at the faces here. I think I only see 2 or 3 people older than me, which is depressing. In my view,
we're retired.
Well, I'm gonna, what I'm about to say is gonna make me sound like I'm 100 years old, so I'm gonna say it anyway. And that is that, in my view, the most obvious change I've seen in my lifetime is maybe up until about right around, I'd say 2000, late 90s, of kind of after the Vortex 1 project. Tornado watch issuance was really supercell watch issuance. If they thought supercells would form, they'd issue a tornado watch. And once we had more Doppler radars around and we're seeing a lot more mesocyclones that weren't tornado producers, we did the Vortex 1 field project. Similar conclusion, we were finding more and more storms that checked off all the boxes, except they didn't have a tornado, but they looked like they were supercells and they had all the other threats. Tornado watch issuance kind of evolved away from just looking for supercells, but actually looking for tornadic supercells. And now you often see severe thunderstorm watches issued in cases in, I'd say late 1990s would have been tornado watches, where the watch discussion will say, supercells are expected, but we're not expecting tornadoes, only large hail.
Yeah, I'm curious if that's why, because the Great Plains saw one of the biggest increases in severe thunderstorm watches, but one of the biggest decreases in tornado watches into the 2000s. So I'm curious if that has.
I think that's exactly it. Yeah. But overall, you showed that the total number of severe thunderstorm watches declined, though, right? It didn't go up.
It has. And I think too, because again, when they issued this county-based warning method, they started doing the watch extensions. So I'm curious if like before, maybe they would have issued 2 separate watches, and now we're just issuing 1 watch with a watch extension. So now that only counts as 1 watch as opposed to 2. So that may have something to do with the recent decrease.
Do you think any impact from the change in the criteria from hail may have also changed that some? Because it didn't seem like it's close to that 1 peak.
Yeah. Do you know what year that was? I'm curious. I'm not
now
sure.
You're putting
That's
me
something
on the
I could
spot.
look into.
Yeah. I thought it was, see, time flies for me, but I'm thinking it was about the early 2010s.
Okay.
I'm gonna guess 2010, but that's just because I'm not Googling.
Yeah, I remember when we were working on this, we had like tried finding the years that the criteria changed and stuff, and that's just not something that anyone is keeping track of. So we know that like changes have occurred, but exactly when, what the date was, and how that has influenced stuff.
2010. He was right.
Old man got it right. Have you looked at like the introduction, the evolution of cams and maybe tightening up watches and their consideration of, if they're going to flip a coin on a given day, the cams are so important now.
Mm-hmm.
Yeah, John, I was thinking the same thing, that my sense is, and I can't ask somebody from SPC because no one's here on the Zoom, but my sense from being out in the field and watching their behavior firsthand is that nowadays it's pretty much unheard of for a tornado watch to come out and for no storm initiation to occur where it's a complete burn. And I think they won't issue a tornado watch anymore until they at least see the cams initiating convection.
Yeah, that's
watch will come out before there's initiation, but there's at least a strong signal in the cams that there'll be initiation. Whereas I can't even tell you how many days in the 90s I chased in tornado watches and there wasn't even a cumulus cloud. That just doesn't happen anymore.
Mm-hmm. Okay. Interesting. Yeah.
You might be wondering why I was chasing no cumulus clouds.
Yeah. Well, I know we had more than one case here where they put out watches and we were just so effectively capped, it was like 12 degrees at 700 millibars or something, and I talked to them and they said, well, it's the models are putting out 40,000 joules of CAPE and, all this other stuff, but there wasn't anything going on. So as the models got better, I'm thinking maybe that has something to do with the drops in the number of watches.
Mm-hmm.
Thanks so much, Callan. Really appreciate you
very
taking
good.
the time to chat. This is awesome. Well, our final presentation of the day, last but not least, my good friend Grant Lashott. Grant is a senior meteorology student at Penn State. He worked with meteorologists from the Aviation Weather Center and the Kansas City Center Weather Service Unit this past summer through the Howling Scholarship Program. He's going to be graduating in May and is planning to pursue graduate school opportunities in aerospace or in meteorology this fall. He plans to pursue a career related to aviation meteorology, especially within the government, and it probably follows pretty clearly that his presentation is related to aviation. His talk is entitled, Using Historical Analogs to Forecast the Potential for Large Volume Air Traffic Days Across Kansas City Center Airspace. So Grant, go ahead and take it away.
Awesome, cool. I don't have like the Zoom up because I have 2 screens. So if something's going wrong, just yell at me because I can't see the chat. So cool.
So far, so good.
Awesome. Good. And you can just see the regular PowerPoint. You can't see the presenter view.
Correct.
Good. Good. Okay. Cool. So thank you for that introduction. I'm really happy to be giving this talk here. I think this is the 4th time total I've given this talk in the last year. So it's really fun telling people what I did basically over 9 weeks of my summer. So let's go ahead and get started. So first, I kind of like to motivate why I spent 9 weeks of my summer doing this. And it's basically that meteorologists are really important for the national airspace system because weather accounts for more than 60% of delays within the system. And not only is this costly in time, but more than $20 billion are lost every year in the economy because of the costs related to delays and cancellations within the system. And convective weather is the most disruptive type of weather. Although winter weather is disruptive, convective weather has a lot more hazards that are dangerous to aircraft, like microbursts, low wind shear, stuff we've seen over the past few years. The image on the right is actually from 3 years ago now, where a plane decided to core punch a storm at like 13,000 feet, which obviously wasn't a great idea. And this actually happened over the past summer, I think in July 2020, a plane on descent into one of the New York airports had to do an emergency landing after going through a hail core below 10,000 feet. Or it was on its descent, and it was a pretty dicey situation from what I understand. So you can see that this is an issue, but fortunately, there's a lot of mitigation due to disruptions to convection due to the collaboration within the National Weather Service, most notably between the forecast offices, the 21 center weather service units, the AWC, and the National Aviation Meteorologists at the command center, the FAA command center in Warrenton, Virginia. And with all that collaboration, one of the products that comes out is the TFM, or convective forecast, or the TCF. And that product is used in the decision-making process. So you can see here's the TCF that's released. I picked one of the days in July from this past year. You see quite, I would say, busy map on the left, and on the right, the operations plan released by the FAA traffic planners at the command center with the en route initiatives that they came up with based on that forecast. So you can see here that this is kind of one way that meteorology is kind of being applied to something that's going to be really impactful for it. So I wanted to think of a new approach to helping the air traffic community with weather, and that was using historical analogs. So if pattern X is happening today, and when pattern X happened in the past, thunderstorms occurred in the afternoon, then thunderstorms will occur in the afternoon today. That's typically what is used when you're using historical analogs for forecasting. So just applying that to air traffic. If pattern X is forecasted to happen today, because the city center had a large volume day the last time pattern X happened, then there'll be a large volume air traffic day today in Kansas City Center based on this weather pattern. And this was chosen because we wanted to see the impacts of weather on transcontinental traffic, because usually when you have large weather systems impacting an airspace that deals primarily with transcon traffic, you're going to have pretty significant issues. So kind of taking a look at the patterns, I did this all myself. I was just given a list of the top 25 largest air traffic volume days from 2017 to 2019 across Kansas City Center. And really only just recent years to kind of avoid bad large air traffic volume days perhaps from like procedure changes. And on those days, I looked at synoptic, mesoscale, and surface weather features across CONUS for each of these days. So kind of just some broad statistics about those days. On 24 of the 25 days, there were multi-cell thunderstorms either in Kansas City Center, usually towards the beginning of the period, and in the surrounding airspaces, definitely towards the later portions of the day. On 15 of those 24 days, you had MCSs, so you had large aerial extent multi-cell thunderstorms that were blocking large chunks of airspace. And perhaps the most crucial finding of me looking through these days was the next two bullet points, in that you had 13 of those 15 MCSs occurring between 3 and 15 Z, so they were overnight. And on 19 of the 24 days that had convection, that convection lasted overnight. So I remember my mentors reaching out to me at the beginning saying, when you're looking at these days, make sure you look at kind of situations where convection lasting overnight, because the models tend to not do a great job at keeping it alive during the morning hours. And then that's when we start running into issues, because we might issue forecasts for this convection to die out 13, 14 Z, and it's still persisting and we got it wrong. So that's what I kind of looked for, and that's why those statistics kind of popped out. And despite being in the middle of the country, 2 of the 25 days featured tropical systems. So landfalling systems in the Gulf had weather east of Kansas City Center that was impacting traffic to some capacity. So kind of after determining what happened at the surface, I looked aloft using the ECMWF era fiber analysis data, because I needed a high temporal and spatial resolution kind of reanalysis construction of these days. And kind of before we do the meteorology here, I just wanted to show you kind of like that typical high volume day was across Kansas City Center. You can see this is a 12Z from a June day in 2019. You have this large complex moving across Minneapolis Center and can't fly through that. So that's one of the reasons why Kansas City Center was probably experiencing large volume day. You had to go around that. And as a result, the bottom portions of Minneapolis Center was a saturated airspace, so traffic was starting to have to leak through the top portions and middle portions of Kansas City Center. So what was happening synoptically? Well, I'm going to show you some maps here. Kind of the typical scenario is super meridional flow. You either had a closed low entering the Pacific coast, and downstream of that, a short wave that was keeping the system alive, or kind of an exact opposite scenario. You had some large high parked over the Southwest United States that still was making the upper air pattern conducive for multi-cell development on these kinds of days. And I also took a look at 850 millibar temperature advection because I realized on pretty much every single one of these days, there was some sort of warm air advection going on. And I think this was crucial to keeping most of the convection alive, that it wouldn't have been able to stay alive otherwise. And of course, I looked at a few mesoscale ingredients. Most important, I thought, was the 850 millibar jet, so the LLJ. And it was present on most of these days, kicking at least 30, 35, 40 knots across parts of Kansas. Again, I think allowed some of these MCSs to continue into the later morning hours. So now that we've kind of seen the ingredients, I kind of took a look at the storm environments. With that, there was often sufficient instability on most of these days, sufficient moisture, nothing you wouldn't be surprised to see when you're forecasting some kind of severe weather to happen, other than really strong surface-based SIN. So you often had surface-based SIN greater than 200 joules per kilogram. And especially, that might not be a surprise during the overnight hours, but the average LFC height was between 700 to 600 millibars on some of these systems. And dynamically, these storms were often sufficient for multi-cells to pop up with, wind shear from 0 to 6 between 20 and 30 knots, and a decent chunk of synoptic support on that front too. And here's kind of, I know I just kind of word vomited a lot of meteorology. So here's kind of the typical sounding you'd see from these systems. You have a lot of stability from the surface up into the kind of lower middle part of the atmosphere. So that had to be overcome, and these systems were still able to kind of get through that. So kind of having all this information in my head, especially for the 25 days I had, I started to think, well, putting these onto a grid and then comparing it to, either model or wrap fields or, something that was analyzed was going to be computationally inefficient. So I decided to use specific observing locations, 13 airports and 13 NWS WFOs on the ground across both Kansas City Center and the surrounding airspaces, kind of represent my current conditions and what I'd be using as my analogs. So I used a bunch of different variables I'd be used, forecasting for thunderstorms, in addition to some of the synoptic scale stuff I was talking about before. And here's kind of just a graphical depiction of the aerial extent I was covering. And if you don't see an airport circled, it's probably because there's an NWS site there. And I'll talk about why that's important in just a second here. So kind of broad scale, how this matching process worked. I determined that I would use the HER to find any significant convection in or around Kansas City Center. So in order for the analog system to run, I obviously want thunderstorms to be occurring, right? Because that was determined to be the most significant type of weather that impacted air traffic in Kansas City Center. So I defined significant convection as a modeled reflectivity of greater than or equal to 40 dBz, or modeled ecotops of greater than or equal to flight level 320, so that's 32,000 feet. And that criteria wasn't randomly chosen. It's actually the criteria they used for the TCF. So basically, the system will start running when it's determining that could be something that forecasters use to look at the TCF when they're using to forecast the TCF. So I used the 0, 6, 12, and 18Z model runs, obviously, because in the summer, it wasn't going out to 48 hours yet, but it was a longer run, and it still is on the HER. And I just did forecasts. It should be every 3 hours there, 0, 3, 6, 9, 12, 15, 18, 21, kind of just to stretch out time, not doing it every hour. And I also had the program here, as we'll see, it also took into account convection that was going to significantly weaken between 9 and 15Z. So if there's a significant drop off in either the modeled ecotops or the modeled reflectivity, I'd have the program store that. So if it determined there was significant convection going near one of these sites, and I usually said within 75 miles of any of these locations, I had it save the location and time of that happening. So basically, if it was picking up that there was something significant going on near the site, I would have it query the instability table that I have all the instability parameters and the other parameters, and using either the HER model data or the NWS sounding if it was 0 or 12Z. So if the program was picking up that there was significant convection around KOAX from the HER, if it was 0 or 12Z, you would be able to use the balloon data to match that to the analogs I had stored in the MySQL table. And if it was not an NWS site, it would just use the HER model data point at that site. And the matching would only occur if there was more 100 instances per hour of the significant convection. So basically the HERs are really high resolution, right? So it'd be picking out all these basically pixels of that the ecotox were greater than 32,000 feet, or the DBZ was greater than or equal to 40. So I would have to, basically I determined that it took about 100 for it to be a multi-cell system that would be significance to air traffic operations. So kind of having this all in mind, I'll just fly through this a little fast because I know I'm over 10 minutes. I had the HER store the locations where convection was significantly weakened between 9 and 15Z. I also had it run matches for these locations in addition to locations with the significant convection. So if there's anything that I called significant going on at any time of that model run, it would store that location. And then I didn't go over this, but the perfect matches are basically, I had the upper air maps matched with the 0.25 degree resolution GFS using an NCL function. So basically, if the upper air maps were matching well to the analysis data I had to the current model data over basically, I think 6 or 7 time steps, I would call it a perfect match. And if the correlation was greater than 0.88, I'd also call that a perfect match. So in order to kind of score these dates based on how similar they were to past situations, I would ask if this date occurred across the instability matches. Because remember, you can have multiple locations across the instability table that might be having different dates pop out. So then I'd ask the program, did this date also occur across the vection matches? That was also my SKU2 and the MySQL table. And then if this occurred across the LLJ correlations, because I also did the upper air map, the 850 millibar map against the using the pattern correlation function from NCL. And then I also asked if there were any, using the significantly weakened convection matches, if this data occurred across those either. And then if it occurred in the perfect height matches perfect based on the correlation being high or it being matched for a certain number of time steps. And the final scoring formula was basically if there was a bunch of these instances of this data occurring across all these different criteria, and again, the 500 millibar height was pretty important in determining whether this kind of situation would come to fruition. I ended up multiplying the correlation of the height field. So obviously if it just went from 0 to 1, I didn't take any negative correlations. And multiplying that against the instances of occurrence. So basically you end up getting this table that more similar scores representing more similar situations. And with that, I included the statistics of the kind of increase from average to total traffic from that day so that there could be kind of an idea and how that day rated across the top 25 of the dates I was given. So that there could be an idea of maybe this would be an impactful weather day based on, or impactful air traffic day based on what just the HER is doing and based on past situations. So the kind of outcome of this database was I called it the Likely Aviation Convective Hazards Awareness Tool. And basically I used dates from July to kind of calibrate the system. So was the 100 instances really working well? Or was the significantly weakened criteria working well? And Monday, August 10th provided kind of a good opportunity to test to see if me kind of changing around this criteria a little bit would give any meaningful matches. So this is just from one day. Here's the TCF from this day. This is actually the Iowa derecho that was, I actually drove through after, not while it was going on, but I saw a bunch of tipped over tractor trailers. But you can see here the TCF had a forecast of, I believe that's sparse coverage thunderstorms crossing through the bottom portion of Minneapolis Center, which we saw before from another day. It's quite conducive to large volume in Kansas City Center. So right away, I ran the database using all the model data and everything that I just talked about. And on the left is what actually happened, and on the right is the first, the most similar pattern it returned. And you can see, while the coverage might be a little bit different than what actually happened, I think the most important thing here is that it did have the intensity right. So on the right here, there's an MCS crossing through Missouri. This is actually the same day as the Bronson, Missouri duck boat incident, which unfortunately I think a few people passed away from. But you can see that you have the intensity of kind of that MCS lining up, just not the aerial coverage. And then the second most similar day, you have the coverage pretty much almost spot on, but the intensity might not be as well forecasted as it was from the number 1 match. And you can see here that at the top, which I have the matches from, that there's a signal for there to be a top 5 volume day in Kansas City Center based on what was coming back out of this program. I should also say this, that it probably wouldn't be top 5 this year because of the reduced air traffic numbers from COVID. So kind of seeing, you see total traffic numbers here of 6,000 plus, that's not going to be true this year at least. And so here's like the whole table spit out. You can see here it's relatively consistent, at least in the top 4 here, spitting back days that are, their top 5 days in air traffic from just 1 to 25. And I asked for what the traffic numbers look like for those 2 days. And you can see here that, well, the first day is a more normal day that we're seeing this year, right? Those numbers being significantly reduced because of COVID. And the 10th here is the impact day. And you can see that the total traffic is way up from the day before. And hopefully the system would have been able to provide some kind of help in predicting that. Again, I really was hoping that this tool would be used as more of a situational awareness thing more than a verbatim, like look at this and hold this as kind of gospel kind of approach. So kind of a summary here, multi-cell thunderstorms in the airspaces around Kansas City Center with no activity in Kansas City Center resulted in the largest volume days. And there were a lot of nocturnal convection events that the cams don't really do a good job of keeping alive into the morning hours that featured in those days. And almost of those top 10 days featured a combination of morning convection and afternoon convection. So you had morning stuff that kind of died off around noon, and then right around 4 or 5 o'clock hour, you'd have more stuff coming in and lasting through the kind of into the next day, basically. And the nocturnal convection that lasted that 11 to 16 Z time frame often ended up coinciding with the west-east transcontinental morning departure banks. So it just so happens that when you had that morning convection doesn't have great timing with the transcontinental push of traffic from each coast. So you can think about it as, you have traffic leaving the East Coast and the West Coast at certain times. And by the time it's in the middle of the country, you still have this convection ongoing, and it's just not a good situation with the amount of volume you have combined with the amount of space you have to move that volume. And I just want to acknowledge my team of mentors who are really helpful in putting this project together and letting me kind of run with it and see what I got from it. And the general hope is that hopefully way down the line, this could lay the framework for someone actually doing like a SIPS level kind of analog database for the entire country that could be used to help for air traffic volume management. And I have to acknowledge that this project wouldn't have been possible if the Ernest F. Hollings undergraduate scholarship program. So with that, I know I went way over time and I'm sorry, and I'd be happy to take any questions.
Hey, Grant, not a question, as a comment. Yeah, that sounding you showed of in the inflow of the nocturnal storms that had the very high LFC. Yeah, we see that stuff a lot. But the stuff goes on and on. It's because the cold pool is 4 kilometers deep. So everything's going up over that mountain of isotropes.
Yeah, my team of mentors basically, they said the same thing. And I was just like, it's insane how that stuff can just keep going. And I remember at one point they were telling me like, maybe you could use isentropic surfaces as like part of the analog. And I was like, well, I don't know if I can grab that, but it's interesting that you say that.
Yeah, so if you had no storm to begin with and that sounding, you'd need nuclear detonation to get parcels to the LFC. But once you've got existing convection and its own cold pool, as long as the cold pool's as deep as the LFC, parcels will get to the LFC. There's no way they can't. Awesome. The only way to kill it is to basically outrun the Cape.
Yeah, that makes sense. Wow, that's insane to think about.
Anything else for Grant tonight? Well, Grant, thank you so much. Appreciate it. Very nice presentation. That wraps it up. I think the worst prediction of the night was that I thought we'd be done by 8:30, and it's now 40 minutes after that. So I'll go ahead and take the humble pie, as I alluded to at the beginning. But again, thank you so much to our presenters tonight. It was awesome. Whole lot of fun to see the great work that's going on, and excited for this to continue at least annually, if not perhaps biannually, as I know we have a lot of students involved. Students, if you could continue to tell your friends, spread the word, bring students to our activities. We really want to have this be a nice opportunity to connect between the students and the professionals. And again, would like to just acknowledge the March 1st speed mentoring session. So again, look out for reminder emails about that this week. Bruno and I will get our heads together and send out some more reminders for both mentors and for students. And maybe we're also considering possibly doing some sort of social activity mid-March timeframe to kind of split the difference between now and the end of March, when we're scheduled to have Dr. Forbes speak to us again. But again, thank you everybody so much for joining us tonight. It was awesome to see everybody. And feel free to hang out if you want to for a little while, just to kind of catch up and hang out. But otherwise, have a good rest of your week. Stay safe in the ice. And we'll see you guys, if not March 1st, sometime, hopefully mid-March or late March.